So we're going to continue working with binomial distributions, and we're going to talk about the mean and standard deviation of a binomial random variable. So for a random variable, let me specify a binomial random variable. Yeah, binomial random variable. And with this binomial random variable, I'm going to assume that we have n trials and a probability of success of p. So these are the parameters, is what they would call it, of this distribution. Then I can specify a couple things here. What does mu represent for a distribution? Does anyone remember?
The mean.
The expected value.
The mean.
Or the expected
Perfect.
value.
Mean / expected value. How about sigma squared? Do you remember what that represents? Someone different.
The variance.
Yeah, variance. Well done. And if I take the square root of the variance, I get the
Deviation.
Standard deviation.
standard deviation. Thank you. Now the mean, this is going to be nice. Because you remember when we dealt with the mean of a random variable in section 5.1, we had to do all this stuff where we had to do x times p of x and then add it all up. Yeah. And then for the variance, that was even more of a pain. You're going to like this, but you have to keep in mind that it only applies to binomial random variables. So mu is going to be n times p. Wow, that's just so cool. It's just so nice. And now let me take note of you, or for you, that if p is a probability of success, q equals 1 minus p. It's a probability of failure. So the variance is going to be n times p times q, or you could write it as n times p times 1 minus p, doesn't matter. The standard deviation is just going to be the square root of that, square root of n times p times q. So there's your mean and standard deviation. Nice. Let's look at a couple examples that relate to this kind of stuff. And the first thing I want to look at is example F. So it's on, again, it's on your handout. And just because these are lettered in order doesn't mean I'm going to cover them in order. So let's jump up to example F. Says, assume that different groups of couples use a particular method of gender selection and each couple gives birth to one baby. This method is designed to increase the likelihood that each baby will be a girl, but we'll assume that the method has no effect. So the probability of a girl is 0.5. Assume this group consists of 46 couples. Complete the parts A through C below. So the first thing I want to do is look at and decide whether or not this represents a binomial random variable. So do we have a fixed number of trials here?
Yes.
Good. There's 46. Are the trials independent?
Yes.
Cool. Are there two outcomes? Don't make Molly do all the work here.
Yes.
Yes, boy or girl. And is that probability the same all the way through the experiment? All 46 couples?
Yes.
Yes.
Yeah, we're assuming that, right? That's an assumption that the probability of a girl is 0.5. Okay, cool. So what else do I need here? Well, I need that n equals 46. Probability of success is 0.5. Nice. So it says find the mean and standard deviation for the number of girls in 46 births. So let's do part A then. A, n is 46, P equals 0.5. That means Q equals 1 minus 0.5, which is again 0.5. How many girls do you expect out of 46 couples? Or from the 46 couples?
23.
23. Good. And the standard deviation is going to be the square root of 46 times 0.5, which is your P, times 0.5, which is also your Q. And that's going to be about 3.39. Okay. So there's your mean. There's your standard deviation. Okay.
And then do we just square root that for the variance?
If you wanted the variance, you would square this.
Or square, sorry.
Yeah. So the variance would be 11.5. Should be. You can double check me on that because I was never very good at math. LOL. Okay. Let's look at part B. Part B says use the range rule of thumb to identify the values separating the results that are significantly low or significantly high. So as a reminder, the range rule of thumb was this. It's mu minus 2 sigma to mu plus 2 sigma. Okay, so let's do that. And I'm going to do it on my graphing calculator here. Let me clear out this, this junk here. Clear that, and then clear this. Okay, so mu was 23. So, why is it giving me that down arrow there? So 23 minus 2 times 3.39. So I get 16.22. And then I want to do that same calculation except with plus here. So one way you could do that is you can just go up a couple, press enter, and that'll bring that calculation down here. And I'll go back and make that a plus. Some people call it lazy. I prefer to think of it as economy of movement. So there
Thank you so much. That is going to save a lot of time. Yeah. All about efficiency.
It is. So this is what the range rule of thumb says. Well, let's be careful. Can I have 16.22 girls out of 46? Can I have that many girls? No. So 16.22 and 29.78. So for all practical purposes, what are the results that I can have that are in this range? What are the typical results?
Between 16 and 29.
Not quite. 16 would actually be here. What number is going to be here that I can get? Joe?
17.
There you go, 17. Now, is 29 going to be like your typical? Or is it going to be atypical? Where does 29 go?
Typical.
Good, 29 is going to be here. So 29 is going to be typical. So when you hit 30, that's going to be your atypical. So that's going to be where significantly high starts. So this is significantly high. And this is significantly low. So that's the boundaries for those things. Are we okay with those? You have to think a little bit, because when you do a range rule of thumb, you're not getting nice integer values, but your results can only be integer values. Quick test question for you, Alex. Is this variable, is a binomial random variable a discrete random variable, or is it continuous?
Oh, okay. Significantly low, significantly high.
It has nothing to do with significantly low, significantly high.
Oh, okay.
The values it can take on. Can it be anything in this range, or can it only be certain countable values?
It can only be the countable values, so it would be discrete.
Yep, it'd be discrete.
Yeah.
Cool. Now the last part of this, thank you, Alex. The last part of this is right here. Is the result of 33 girls is that significantly high? So we'll do that part first. Is 33 girls significantly high?
Yes.
Yeah, because it falls into our significantly high range. The second part is, what does that suggest about the effectiveness of the method? Well, there's two possibilities here. Remember at the beginning of this, we assumed that the method had no effect. And so let me kind of underline that a little bit. Had no effect right there. Now, if it had no effect and we got a result of 33 girls, well, one of two things happened. Either we saw something that was significantly high and very unusual, or the other possibility is that our assumption was wrong. And for this course, what we're going to do is we're going to assume that if we see these significant events, that our assumption was probably wrong. We could be mistaken in that, but that's the choice we're going to make. Because the chance of being wrong under this assumption and getting 33 girls is pretty small. To get 33 girls would be very unlikely if there's a 50-50 chance of a boy or a girl. So we probably saw the effectiveness of the method. That's what we saw. That's what's accounting for such a high number of girls. It seems as though the method is effective. Yay. Comments or thoughts on that one?
I don't quite understand why, or like where the formula for the variance and standard deviation come from. Could you kind of like, I don't know if there's like an intuitive way of explaining it. Why do we multiply by Q?
Why do you multiply by Q?
Mm-hmm.
You know, boy, I haven't thought about that kind of stuff in a long time. I think some of the derivation of this stuff probably goes beyond our course, but it certainly goes beyond me at this very moment. I seem to remember some stuff in the advanced probability classes I've taken about moment generating functions, but that certainly goes beyond this course.
Okay.
That's just something that you're going to have to accept. You're just taking it on in good faith. But at least this part seems to make sense. I mean, we did this last week. I said, all right, we've got 10 girls or 10 babies being born. How many did you expect to be girls? And intuitively, everyone just yelled out 5. And the reason was because 10 times 0.5 gave me 5. Here, 46 times this, it seems to fit with our expectations. Now, as far as the standard deviation is concerned, yeah, that one I can't help you out off the top of my head. And I don't think that the answer lies within the realm of this course. Yeah,
Got it.
it's a great question. I wish I had a better answer. Yeah, but right now,
Mean makes sense.
this is a grad level thing, and Mimi's who's taking this stuff much more recently than me is saying, yeah, that's graduate level.
Yeah, we derive it in grad school, so don't worry about it.
Yeah.
Take his word for now.
Thank
Believe
you.
me, I don't distribute fake news. Okay, that was it's the way it's done. So, okay, let's keep going. We'll back up and do example E. So again, kind of going back to some probabilities, and then I'll have you calculate a probability as well. So example E. Let's find that on our little sheets here. Example F. There we go. A survey showed that 72% of adults need eye correction. So let me kind of highlight that a little bit. 72% of adults need eye correction. If 22 adults are randomly selected, find the probability that at least 21 of them need correction for their eyesight. Is 21 significantly high number of adults requiring eyesight correction? So this one, we're not going to answer with the range rule of thumb like we did the last one. This one we're going to just answer by calculating some probabilities. Let's first decide if this meets the criteria for a binomial random variable. So is there a fixed number of trials?
Yes.
Yes.
Yeah, there's a fixed number of trials. There's 22 of them. Are they independent?
If they're random.
If they're random, the other thing that they have going for them is that you can definitely apply the 5% rule. The 5% rule we've translated into multiply by 20. 22 times 20 is 440. So, well, 440, I think that there's a good chance that of the adults that we could survey, that population is greater than 440. So you can use the 5% rule, which means that you can assume that they're independent. So we got independent nailed a couple different ways, is what I'm saying.
Okay.
So we're good there. Two outcomes. Are there two outcomes for this kind of procedure?
Yes.
Yeah, you need them or you don't. So we're good there. And same probability, that's coming from our 5% rule, all right? Our population is big enough that, you know, the dependence that we get is really not going to change the probability in a meaningful way. So this is a binomial random variable. Binomial random variable. So the things I need are that N is 22. P was what, 0.79? Take a look back, no, 0.72. Good thing I checked. P is 0.72. Now, what probability do I gotta calculate here? Well, I want to calculate the probability that at least 21 of the 22 adults require eyesight correction. So that's going to be this one. Probability that X is at least 21. What notation would that imply here?
Less than or equal to 20.
Actually, no.
Greater than or equal to 21.
At least 21. Good. So that means at least 21 is greater than or equal to. So good job, Joe. So that means X equals 21 or X equals 22. And because these are mutually exclusive, I can just add those up individually. And I mean a plus there. plus x equals 22. Ah, my handwriting's getting worse as the lecture goes on. Let's calculate these in your favorite way. You can either do it off of Google Sheets or you can do it on your graphic calculator, but we need to add up these two probabilities. So let me do that over on Google Sheets. I'm just going to put it kind of in any random spot. We don't need it any place special. Equals binomial distribution. Number of successes would be 21 out of 22 possible. Probability of success. Do I have this in the right order? I'll find out in a minute. Probability of success is 0.72, comma, false. Yeah, I look like it. Got it. So that's the first one. Binomial distribution, 21, comma, 22, 0.072, and false. I got to do that again for the probability down below. What's the one thing that's going to change from the first one to the second one? First one is the probability that x equals 21. What's the one thing that I'm going to change? I'm going from the
Would you
first
make it x equals 22?
Yep, got to make it equal to 22. So I'm just going to copy this to come down here. And then I'll click on that cell and change that 21 to a 22. I think that was Joe that gave it to me. Thank you, Joe. So wow, that probability got even smaller now. Now that's great that I got those two probabilities, but I need to do a little bit something else with those as well. What's that last thing I need to do?
Add them up.
Yeah, add them up. Good. So fortunately, there's a sum command. Just type in equals sum, click and drag on these two cells, and there you go, 0.06 or 0069. Yay. Looks good. That's your probability right there. 0.00694. Are you able to match that probability calculation? You could do it off your graphing calculator if you want to do it there too. That'd be fine. No preference for me as to which one you should be able to do, just as long as you can get that probability one way or another. Doing okay there? Okay. Let's back up to problem number D and take a look at that one. And I'm probably gonna have you work on this one just to see if you're as good as you'd like to be. And what we'll do with example D first is we'll run through and decide whether or not this is a binomial distribution. Does this represent a binomial random variable? So we have to check a bunch of things to see if it works. So what's the acronym that I'm going to use to check things here? Does anyone recall what that represents or what that acronym was? Fits. Thank you. So I want to check that it has a fixed number of trials, that they're independent, that I have two possible outcomes, and that the probability of success stays the same throughout the trial. So let's make sure that it fits. Well, for example, D, are there a fixed number of trials?
Yes.
Yes.
Yes, you got 11 of them. Are they independent?
I'd say yes.
Got a vote for yes from Alex. Bradley, what do you think? Are they independent?
Yeah.
Okay. Now, there's a couple ways you could arrive at the conclusion of independent. So one of them is that, you know, whether or not somebody uses a cell phone in a class is going to be independent of somebody else, assuming that they're selected at random. The other way is with our 5% rule. I mean, it's such a small sample. As long as your population is more than 220, then you can use the 5% rule. Either way, you get that they're independent. So thanks. Are there two possible outcomes? Yeah, you either use it or you don't, right? So we're good there. And last but not least, the probability of success. The probability is going to be 59% for the whole trial. So these are the two numbers that you're going to need as part of your work. I think we're going to need one more here as well. It says, if 11 adult smartphone users are randomly selected, find the probability that fewer than 4 of them use their smartphones in meetings or classes. So probably that X is less than 4. And we've seen something like this before today. Let's see if you can't calculate that on Google Sheets. So we'll go back to here, and I'll give you a little bit of time to do that. Maybe I'll take advantage of this a little bit. Paste that here. I don't know if I need to bother to go down to 11, but see what you can do. See if you can't find the probability that X is less than 4. Like I said, I'll give you a couple minutes to work on that. So there's a couple ways I'll show you to calculate this. The first way is going to look like this. I'm just going to calculate the probabilities, and I only need the first few. So I'll type in binomial distribution, and then of this, comma, there's 11 in our sample or 11 in our trials. And a probability of success was 0.59, and I'll type in false here. And then I'll drag this down. I really only need to drag it down to here because I want to add up the probability that X equals 0, 1, 2, or 3. So if I want to, I can just type in equals sum of these variables, excuse me, of these probabilities. And there you go, 0.03425, and a lot of you were getting that, that's great. The other possibility here is I can just come right to here, equals binomial distribution of this, and I guess I could just type in the 3 if I wanted to, because I don't really need to copy this command anywhere. 11, comma, 0.59. Except what am I going to do different? Does anyone know? I'm going to type in true.
True.
And that's going to add up all the probabilities, including X equals 3 and lower. So yay. So it's a different way to get this, but both of them work. And you can do the same thing with binomial PDF and CDF on your graphing calculator. While doing it with PDF would be really, really tedious. So are we okay with that one?
Yeah.
Let's finish up this way, because this one's been killing me for about a week. I've had a bag of M&Ms staring me in the face. So just so you know, went out and spent big bucks for you guys. Do a live demonstration. We're going to take a look at some M&Ms. Now, these were actually first produced in World War II. and given to the soldiers because they didn't melt. Melt in your hands, melt in your mouth, not in your hands, right? That was the old slogan.
Mhm.
And let me put in some numbers here for us. Now, I sent you this link in the chat earlier. So let me go back to that. I think it's up here. There we go. And here's my observed values for all these M&Ms. And I could treat each one of these as kind of a binomial random variable, binomial random experiment. Now, M&Ms are made in 2 different plants around the country. There's one in Hackettstown, New Jersey, and one in Cleveland, Tennessee. Yeah, I know, that doesn't sound right to me either, but whatever. Cleveland, Tennessee. Now, the probabilities of M&Ms or their color distribution from the Hackettstown, New Jersey plant, which is what services us, are these. And if you can tell, or if you can't tell, statisticians love M&Ms. There's so much stuff about probabilities in M&Ms. So distribution looks like this. If I wanted to calculate my expected values compared to the mean, well, I could do that. Let me just take, I had a total of 99 M&Ms here this morning. So it's going to equal the number observed, no, it's going to be the probability of a red one times 99. That's how many I expected. What's the standard deviation of how many I expected? Well, that's going to be the square root of n, which was 99, times the probability of success, which was this, times q. Well, q is really 1 minus p. So I'll do times 1 minus this again, 2 parentheses. That's my standard deviation. That's my sigma. And what I can now do is I can calculate the range rule of thumb for my data. So I can say, all right, well, this is going to equal the mean minus the standard deviation, or actually minus 2 times the standard deviation. And then do the mean plus 2 times the standard deviation. So that's your mean plus 2 times standard deviation. Wow. So I observed 10 M&Ms. Is that unusual for a bag of 99 M&Ms? Well, this is our cutoff for unusually high and unusually low.
Yeah. So it's not unusual.
No. Now the cool thing is I can repeat this calculation by dragging. Let me drag it all the way down. And unfortunately, at least for the sake of entertainment in this class, I didn't observe any unusual events. The M&Ms that I got, the counts that I got, no big deal. Nothing unusual. Not for the, now I'm doing this for the red data, not the data here. Just doing it for this part right here. But again, usual or unusual, that's going to be based on whether or not you're inside or outside the range rule of thumb, 2 standard deviations. Cool. All right, that's all I got time for today. Any questions on what we covered here? Looking good there?
Could you go back and do the standard deviation for the M&M?
Sure. So for the standard deviation, remember, let me see if I can find my sheet here. Oh, where is it? Where is it? I'm not finding it at the moment. Here we go. No, that's not it either. All right, so for the standard deviation, it's n, the square root of n times p times q, which is what I have here. There's my n. There's 99 M&Ms here in my sample. The probability of success from M&M Mars is given at 0.131. The probability of failure is 1 minus the probability of success. So that's where I have the 1 minus B4. So that whole thing, that's my standard deviation. If I wanted the variance, I could square that. But we don't use the variance in many calculations, so we'll just leave it with the standard deviation. Did that help out? That answer?
Yes. Yeah.
Thanks.
Thank you. Appreciate it.
Mm-hmm. Anything else?
What are the differences between the two observed columns?
Oh, this is just a different class. I did that in a different class. So
So we were
yeah.
doing the second column.
What's that?
We were looking at the second column, right?
Yeah,
In the
we're
left?
working with the red data. Mhm.
Okay.
So I could modify my table here to reflect 76. So if I did 76 here, and then I copied that all the way down. Now I've got the expected values for 76 M&Ms, and we can look and see, yeah, I still didn't get any unusual events because everything was adjusted now for this data, but I don't think any of these lie outside of my range of typical values. So good question. Good question. Okay. Well, that's it for today. Keep up with the homework, please. And you got a test on this coming up a week from today. So be ready.